today we are going to have our sixth lecture. The main topic for today would be linear independence. So linear independence of a set of vectors. Now, let me quickly recall the stuff that we had seen so that we would have a better shot at relating two things. So our basic idea was to solve a system of equations. So when we say a system of equation, it is basically like a matrix A, a vector B, and we want to find the vector X, which can help us as a solution for this. So what we did was, we basically went for the augmented matrix, and we talked about things like the rank of the matrix, the pivots, the row echelon form, free variables. So these were like various notions that we had used in order to understand or talk about the solutions of this particular system of equations. So once we did all of these things, then we went on to something we called as the linear span of a set of vectors. And somehow we were able to tie this thing up with solving a system of equations. So the idea is, we had this geometrical concept of a linear span of vectors, and we related it to an algebraic way of understanding that geometric concept. Same idea goes with the linear independence of set of vectors. Linear independence basically came out of a geometrical idea of how to interpret parallel vectors. So for example, if I give you a vector v1, and I give you another vector, say v2, of course from the looks of it we can say these are non-parallel vectors. And the once I have non-parallel vectors, it will be easy for me to reach any point P using just these two vectors. I can perhaps go in this direction further up till here, and then try to go in this direction to reach P. However, if I was given a v1 vector like this and another vector, say v2 vector like this, which is what we call as the parallel vectors, then for us to reach a point Q, which is like starting from, let us say, this point S, it will not be possible for us because our movements are only restricted in one direction. So this is what we call as the concept of parallel vectors, and this we called as the concept of non-parallel vectors. So understanding parallelism is fine from a geometrical point of view, but what if we want to generalize this to higher dimensions and try to make sense of the idea of a parallel system using algebra? So that is our focus. What is we need to show to understand the concept of parallel to algebraic systems? So here is first attempt. When we say two vectors are parallel in two dimensions, or for that matter any dimension, so if I say v1 is parallel to v2, algebraically we mean the following thing. That v1 is some constant times v2. So when we say C is some this is what we mean algebraically, how two parallel vectors would be related to each other. Okay, let's push this a little bit more. From V1 equal to C times V2, we can also write this guy as V1 plus minus C times V2 as the zero vector. So in some sense what we are saying is two vectors are parallel if a linear combination of V1 and V2 can produce the zero vector. So out here C is some scalar, the coefficient of V1 is 1. So we are saying there is a non-trivial linear combination of V1, V2 which can produce 0. Now parallel means it is lying along the same line. So if we go in a higher dimension R3, when do we say that vectors are lying in the same plane? So if I give you two vectors V1 and V2, so how to say algebraically that they live in the same plane? Okay. Now, if we think about this question a little bit, it will help us understand something. So let's see what exactly are we after. So when I say two vectors are given, when will they lie in the same plane algebraically? Well, think of it this way: if I give you two vectors in a plane, two vectors in R3, they will always lie in a plane. They might lie on the same line, or they'll just make a plane. So if I give you two vectors, then they will always form a plane. So in some sense, this question is kind of redundant. If I give you two vectors, what is the condition on so that they both lie on the same plane? However, if I give you a third vector in R3, let me add one more to the list. Say V1, V2, V3. Then it is not obvious at all that three vectors have to lie in the same plane. In fact, they may not even lie in the same plane. Just think of the 3 dimensions, x, y, and z axis. So they lying in the same plane must be something special. So let's ask ourselves this question: when will V1, V2, V3 lie in the same plane? In R3. Okay. So let us look at a sample vector and see what happens. If I am given a vector V1, if I am given a vector V2, we know these guys will always form plane. And I want my third vector to lie in this plane. So what exactly should happen? Now imagine if I am given V1 and V2, I can move in both directions V1, V2. That means every point in my plane is accessible. So that means I can take V1, scale it appropriately. Then I can take V2, scale that appropriately, and we should be able to get V3. So this is what we mean by the algebraic interpretation of having V1, V2, V3 lie in the same plane. So just like before, let's try to rewrite this in a different manner and see what happens. So again, we have been able to capture the essence of coplanarity. So let me write that. word for us, coplanarity. So coplanarity we have been able to achieve by again having the same concept of bunch of vectors combining linearly to produce 0. So vectors combining So we want to capture the idea of coplanarity. And we are saying coplanarity is the same as having a linear combination of vectors produce the 0 vector. Now we have seen two instances in R2 and R3 where we have been able to interpret the idea of them lying on the same line or in the same plane. So we want to generalize this concept, and that is what we are going to call as our linear independence. Okay. So let's capture our definition from things we have seen. So here is our first definition. So suppose we are given a set of vectors S. So V1, V2, Vk. We'll say S is a linearly independent set. If a non-trivial So we are saying that a set would be a linearly independent set if a non-trivial linear combination of the vectors in that set can produce me the 0 vector. So there are a couple of things we would like to emphasize. One is the non-trivial part. What exactly do we mean by the non-trivial linear combination? So first of all, let us see what do we mean by linear combination. Well, recall the span. There we had talked about linear combination. So we are saying, can I produce a 0 vector by combining my vectors and scaling them appropriately? Now, here is a very obvious solution, which I would like to call as a trivial solution. So it is a trivial solution to my problem. Just take C1, C2, all the way up to Ck as 0. So of course, anytime you want to linearly combine a bunch of things, you just don't take any of them, and you are still going to produce a 0 vector. That is what we mean by non-trivial linear combinations. So when I say non-trivial linear combination, we mean at least one of the CIs must be non-zero. So, if at least one of the CIs is non-zero, then we will say non-trivial solution, and in which case, actually, the way I have written the definition is wrong. I wanted to say S is linearly dependent. Independent. S is linearly dependent. So let me add to this. Otherwise, we will say S is linearly independent. So that means the only combination which can produce me the 0 vector, if it happens to be the trivial combination, then we will say the set is linearly independent. So without further delay, let's try to see an example whether the vectors are linearly independent or dependent based on the definition we have tried to capture. Okay. So let us say we are in R2 as usual, and we are given a set of vectors S as, let us say, 1, 2, and say -3, 4. And we want to ask ourselves a simple question. Is S independent or dependent? Of course, when we say independent, we mean linear independence or dependence. But since we are working through linear algebra, everything will be linear until specified otherwise. So I'm going to stop using the word linear and assume that is the case. So what we do is we start with our definition. We have this vector. Let's call this vector as V1. We want to see if the linear combinations or linear combination of these two vectors can produce me the 0 vector. So when somebody says independence or dependence, we are asking that question: can a non-trivial combination equals the 0 vector? If yes, then the set is dependent. If only the 0 combination will give me the 0 vector, then the set is independent. So if you look at this, it should remind you of what we called as a column picture. picture and the column picture of a system of equation. This is basically a column picture. I want to produce two, I have columns, I want to combine them in a way to produce the zero solution. So if I want to interpret everything in terms of matrix, then this is what we are after. We are looking for solutions of this system. Okay. So the question is, if I'm looking for the solution of this system, I know how to solve such a system. Am I just looking for a solution, or am I looking for something more than that? Or maybe I'm not even looking for how the actual solutions look like. Now, one thing is very obvious out here about this system, and that is of utmost importance to us, that this system is always consistent. And the reason being, because if you remember, definitely C1 equal to 0 and C2 equal to 0 is a solution to this. Moreover, if we view it from what we had seen earlier, a system is consistent provided the right hand side in the right hand side column there is no chance of having a pivot. Now, no matter what row operations I do, since both the entries are 0, they will remain 0 no matter what kind of row operations I do. So there's no chance that I will ever have a pivot in the rightmost column. So all my pivots, wherever they are going to be only in the coefficient matrix. So that way I know it is going to be definitely a consistent system. So actually I'm not really interested in solutions because I know one of them exists. What am I looking for is, does this have a non-zero solution? Okay. So in some sense, we are looking for whether this guy has more than one solution or not. From what we have done so far, we know that a linear system will always have either no solution, or it will have exactly one solution, or it will have infinitely many solutions. So in this present case, we already have one solution, and we are looking for whether it has infinitely many or not. So the moment somebody says infinitely many, the thing which comes to mind is basically, the rank of a matrix or the presence of free variables. If there are free variables, then we will have infinitely many solutions. Otherwise, we will have only the zero solution, the unique solution. Okay, so let's try to row reduce our matrix and see where it takes us. So we are going to create a echelon form. So something like this perhaps will help us. So the moment we see that we have got our echelon form, we don't really need to go all the way to reduce echelon form. We know that 10 is a pivot, 1 is a pivot. So we have two pivots. So that means the rank of this matrix is 2. So it has a full rank, hence no free variables. The moment I have no free variable situation, that means it must have a unique solution. Now let me reiterate something. How do I know it has a unique solution? Because I already know it has one solution, namely the zero solution. And now we have guaranteed, because of the rank, that it cannot have more than that one solution. So in this case, we can say it has only the 0, or you can say the trivial solution. So the moment I say it is only 0 and trivial solution, that means the set is independent. So what I would like to emphasize on this is, what we should take from here is that the question of dependence or independence has been basically converted to that of a system of equation. And from the system of equations, we have used our old methods of row reduction, talking about rank, free variables, to figure out whether our set is independent or not. Now, there's another thing that we should keep an eye on, that this is not just any system of equation. The right-hand side is 0. The right-hand side is a 0 vector. So in some sense, we are not after just any kind of system of equation. We are after that system of equation where the right-hand side is a 0 vector, and we have a name for it. We call it the homogeneous system of equations. So when we say AX equal to 0, this is what we call as the homogeneous system. So what we are saying is the solution to this homogeneous system is tied up with the concept of linear independence. Likewise, we had seen that the solutions to Ax equal to b was tied up with the concept of the linear span. So what you should understand from this is that all the geometrical concepts we have mentioned so far, we have been able to somehow interpret them in terms of system of equations. So we have an algebraic way of checking things which up until now were geometrical in nature. Okay. So let's try to further this thing and see if we can improve this to another situation, or can we test it in slightly non-trivial example where things might not be that obvious. So what if I was given some bunch of vectors in R3? Let's try to do this example so that we can better understand it. Suppose I was given, say, 1, 0, 1, 1, 3, 2, and let us say I was given 3, 3, 4. So suppose we are given these bunch of vectors over here. Question is this set linearly independent or dependent? So from our way of writing things, suppose I call this as my vector v1, this as my vector v2, and this as my vector v3. I'm basically asking whether this particular expression or this particular linear combination can produce me the zero vector. So what would be that linear combination? Is it only the zero combination or is it a non-trivial combination? So based on this, we would create our matrix. Right hand side 0. If you observe one thing, since my right hand side is going to be 0 always, so we might even as well drop it from consideration. So sooner, or well, I should say a little later, we will start dropping the right hand side, because that is not what is controlling the row operations. Okay, so let's try and see. I want to reduce it to our echelon form. So here's my first row operation. And this is what we are going to get. This is 0, this is 1, this is 1, this is 0. Now we see there is something peculiar going on. The second and the third row seems to be just multiples of each other. So what if I went and divided the second row by 3? So you get 1, 1, 3, 0, 1, 1, 0, 1, 1. The moment I see this side that two rows are equal, it kind of hints that we are going to lose out on the rank. Our rank is going to be not exactly 3. So if I do another row operation to finally get into the echelon form, so I will have 0, 1, 1, 0, 0, 0, 0. So now I see that there are only 2 pivots, as we had already suspected. The rank is not a full rank. So if we say that these are 2 pivots, the third column is basically the column for the free variable. The moment I see free variable, I immediately know that there will be infinitely many solutions. And since I know there is already one solution, namely the 0 solution, so I'm very sure that it has infinitely many solutions. The moment I see infinitely many solutions, we know that there must be a non-zero combination which will produce the 0 vector. Of course, we want to find what that combination would be, but at least we have been able to answer that this set is going to be a dependent set. So the question is, how are they dependent on each other? Like, what combination is producing me the 0 vector? So we have found that S is a dependent set. So here's another question now that we have answered one question. What is the dependency relation? That means, this is another way of saying, find me that C1, C2, C3, which will produce me the 0 vector in this particular equation. So all we have to do is just solve for the system. We have already got everything taken care of. So from that matrix that we have got, we can say C1 plus C2 plus 3C3 is 0. And C2 plus C3 is also 0. Remember, C3 is our free variable. We we did say the third column is the free variable. So we can write down everything in terms of the free variable. So we can say that C1, C2, C3, this guy is remains C3, this guy is minus C3, and if I plug in the value of, so if I plug in the value of C1, C2 and C3 in there, in the first equation, we will get what we want. So C2 is minus C3, so this will give me minus 2C3. What this means is, I can give any value to C3 I want, and I can produce dependency relations. For example, one of the solutions is minus 2, minus 1, 1. That means if I plug in minus 2, minus 1 and 1, I will get a 0 vector. Or I can multiply this vector by any non-zero scalar I want and produce other solutions to that equation. So once I have one dependency relation, I can produce infinitely many dependency relations. So just to be clear, this is what we have so far. Minus 2v1 minus v2 plus v3 will give me the 0 vector. Okay. Now let us try to increase our scope to answering more questions. Then once we have the machinery to do this. Question is, if I give you a bunch of vectors in a space, can I somehow know by just looking at the number of vectors I have been given, can I somehow tell whether they are going to be dependent or independent? So let me pose the question more precisely. So let me pose the question more precisely. Suppose I am working in R2. Let's start small. If I give you a vector v1, will it be independent or dependent? Just one vector. If I give you more than one vector, we have seen an instance when I gave you two vectors and it turned out to be independent. What if we want to push our luck? Can we have three vectors in R2 which would be linearly independent? Can we have four vectors in R2 which could be linearly independent, so on and so forth? So basically we want to figure out, is there a bound on the number of vectors which could be independent? Or is it like it's free for all, any number of vectors you give, I can possibly find some independence. Okay, what if I was given three vectors? So let me give these vectors some names. So let me say my vector v1 is, let's say AB, my vector v2 is some PQ, my vector v3 is some ST. What if I was given three vectors? Can they form an independent set? So using the definition, I will create this matrix and ask ourselves, what can we say about the solution to this system of equation? So first of all, let us notice there are three columns in the coefficient matrix. Okay, so what about the rank? Can I say, no matter what these numbers A, P, S, P, Q, T are, the rank of this thing can never be more than 2, because I have only 2 rows, so there could be at most 2 pivots. So the rank is going to be 2, then can we say, no matter what these numbers are, there is at least one free variable. just to be clear about how we are achieving this, after row reduction, depending on what these things were, I claim that either you will have a matrix of this form, where you have a non-zero entry over here, doesn't matter what these entries are. So these are our two possible. This is one possible reduced echelon, one possible echelon form that can happen, or you may have a situation like this. Or you may have a situation like this where the entire second line is a bunch of zeros, or you may have a situation like this that both the lines are zeros. So either way, we are guaranteed that there can be no more than two pivots. Either I have one pivot or at most two pivots. So no matter what we do, there's always a free variable. Out here, this is the free column. Out here, the middle column is the free column. So the moment I say it has at least one free variable, that means it tells me that it will have infinitely many solutions. So that means the set must be dependent, because I can always find non-zero solutions to my equation. So the moment we say the set is going to be dependent, what is the conclusion? The conclusion is, if you give me any three vectors in R2, I can always guarantee they will form a dependent set. So in some sense, 2 is that threshold above which things become dependent, below which things may remain independent. So based on this, we will try to further our knowledge, and let's try to make a conjecture, and I'll leave it for you guys to think why that conjecture is true based on the example we just did with in 2 dimensions. And then we can pick up in the next class about that. So here's a claim we are trying to make. So here's a, let me call it a theorem. So I have k vectors inside the space, let us say Rn. If k is bigger than n, then S will be a dependent set. So in other words, what we are saying is, if I have more vectors than the space I am living in, then that set of vectors will always be a dependent set of vectors. So here's a sketch for our proof. As you will see, it is entirely based on the idea we have just seen. So if I have k vectors, here's my vector v1, here's my vector v2, so here's my vector vk, and here I will have the zero vector. So number of columns is k, and number of rows that we have is n, because each vector lives in n dimension. And we are given that n is less than k. So we can say for sure that the rank of this matrix would be no more than n. So if it is no more than n, then we can definitely say that at least k minus n free variables. So even if we have all n pivots, whatever is the difference between k and n, we will have that many free variables. And that means I will have infinitely many solutions. So in particular, I will have a non-zero solution, and hence my set would be a dependent set. So in fact, I have given you pretty much the proof, except for filling it with appropriate words. This is more than a sketch. But one thing is good about this theorem is this is going to be of much use to us as we move along. This is actually going to help us define what we call the dimension of a vector space. Had it not been for this theorem, the concept of dimensionality would have been not well defined. So we will be using this and the idea of a linear span to further talk about these things.